Okay, we're going to start into chapter 6, which is dealing with the standard deviation. So, my first question here is a student took both the ACT and the SAT. She scored 30 on the math ACT. She scored 680 on the math SAT. On which test did she do better? I know you guys are more familiar with the ACT. The SAT is a test mostly on the East Coast and the West Coast. A lot of schools take the SAT. In the middle of our country, we tend to take the ACT. So, how would you know this? You know, which one was better? So, we're going to have some information. Some of the information we're going to need to know is what's average, what's common, what's the average score, and also we would need to know the standard deviation. So here's the information that I have. I don't know which particular year this was, but the ACT, this is the mean for the math, and this is the standard deviation for the math. And for the SAT, I have the mean and the standard deviation. Now you'll notice I use some different symbols. We had been using before X bar and S sub X. And these are called sample statistics. So X bar was the sample mean and S sub X was the sample standard deviation. Well, mu, and this is a Greek letter mu, and it would be mu. And so mu is the population. That's the whole, everybody who took the ACT. That's the average math score, not just a sample. So if we were talking about just our class or our school, we could consider that a sample. So we would use X bar and S sub X. If you're dealing with a whole population, then you would use these are called parameters, population parameters. These are not statistics. Statistics are when you draw a sample and then you summarize from your sample. So these are population parameters. This other symbol is sigma, and that's the Greek letter that we use for the standard deviation. So I have this information, and now I have to have a way that I can compare those. So when I think about which one's better, is it better to have a 30 with this mean and standard deviation, or is it better to have a 680 with this mean and standard deviation? So what we do is we have to kind of put it on the same playing field. And so we're going to do something called a z-score. And when you calculate a z-score, the way you do that is we're going to take the raw score and we're going to subtract the mean, the population mean, since we know it, and we're going to divide by the standard deviation. This is called a standard normal calculation. We haven't really talked much about a normal model and a picture of a normal model, but we're going to be doing that next. So what I want to just talk about now is how we can kind of compare two different distributions. So for the ACT, to calculate the z-score, I take the raw score, which we had was 30. I subtract the mean, which was 21.0. And I divide by the standard deviation, which was 5.3. Now, typically we would round to 2 decimal places if we need to round. So I have 1.70. For the SAT, I'm going to take the raw score, so she got a 680, subtract the mean, and divide by 116, which was the standard deviation. And when I do that, I did it already, and I get 1.42. Now, what this means, how you interpret a z-score, this tells us that she scored 1.7 standard deviations above the mean. And this one, 1.42, tells us she scored 1.42 standard deviations above the mean. It's possible to have a negative z-score. It's possible to score below the mean. That's a possibility, and that shows up as a negative z-score. So when we want to consider which one is better, well, it's better to score more standard deviations above the mean. This is a higher score. So she did better on the ACT. Now, why would you want to know that? Well, if you were applying to a college and the college would accept either the ACT or the SAT, you might want to just report your ACT score and not your SAT if you did better on that. So that would be a situation where you might need to know that. All right, another thing that we need to know, this is cut and paste from page 105 in your textbook, is we have to know how our statistics behave if we add data values and different things that can affect the mean, the standard deviation, the median. So we're going to look at some of those things. So one thing, and I highlighted this, so we're going to do an example in just a minute. When adding or subtracting a constant to each data value, all the measures of position, your center, your percentiles, like percentiles would be like your quartiles as well, because like you could talk about the 25th percentile, which would be Q1. That means 25% of the scores would be at or below that value. Your center can be your median or your mean, your min and your max. All those things are going to increase or decrease by whatever that constant amount is. But the spread is different. If you add or subtract a value, imagine if you had a histogram and you added 12 to every value in your data set. Your entire histogram is going to shift. So your centers and your positions shift, but it's not going to be more spread out. So your measures of spread do not change. So adding or subtracting a constant to every data value adds or subtracts the same constant to measures of position, but leaves measures of spread unchanged. Then if you multiply or divide all the data values by a constant, then all the measures of position will also change. They're going to be multiplied by that same value. And this time, so does the spread. So that's important. We're going to look at this in just a minute. The other thing to keep in mind when you standardize into z-scores, which is what I showed you how to do, it does not change the shape of the distribution of a variable. So if I took my ACT scores, my raw scores, and looked at the distribution, and then if I changed it to z-scores, the distribution is going to look the same. What a z-score does is it changes your mean to 0 and it changes your standard deviation to 1. And that's what allows us to compare different distributions that have different means and standard deviations. And then a little reminder here before I do some examples, a z-score measures how many standard deviations your data value is above or below the mean, like I did on the ACT and the SAT problem. So we're going to do an example. Suppose the class took a 40-point quiz, and the results show a mean score of 30, a median of 32, an IQR of 8, a standard deviation of 6, a minimum of 12, and Q1 is 27. And we're going to suppose you got a 35. So I have the data in this chart. So I listed all the original. So this is a quiz. This is the class mean, the class median. So right away you might think, oh, wait, the mean's lower. That might mean there's an outlier or skewed to the left. It could mean. IQR is 8. That's remember, that's Q3 minus Q1. The standard deviation is 6. The minimum is 12. Q1 is 27. Your score is 35. So this is what we're dealing with. Now, what we're going to do, I decide to weight the quiz as 50 points, and I'm just going to add 10 points to every score. So your score is now 45. So what's going to change? So if I'm adding 10 and your score is now 45, remember adding a constant, the measures of center and position will change. So the mean is a measure of center, so it will change. So I'm going to add 10 and I get 40. The median is a measure of center, so it will change. I add and I get 42. The IQR is a measure of spread, and so is the standard deviation. These will not change. Again, imagine the histogram of all the scores. The entire histogram moves, but the shape doesn't change. The minimum value will go up by 10, so it will be 22. And Q1 is a position, not a spread. It will go up, and it will be 37. So that's what we would get for those scores. So adding a constant, the measures of position and the measures of center will go up by that amount. Measures of spread do not change. So that's what was meant from this slide here that I talked about. So next, I decide to weight the quiz as 80 points. So instead, I'm going to take your raw score and I'm going to double every score. So I'm multiplying by 2. So here we go. The mean, instead of, and I said what your score was. Your score is now 70. So the mean will double, and it will now be 60. The median will double. It will now be 64. Now, remember, these are measures of spread, but if you look at our notes from this, it said when you multiply or divide all the data values by a constant, all the measures of position and the measures of spread will change by that amount. So this time we do double it, and we get 16. We double the standard deviation, we get 12, which means my data is getting more spread out. I double the minimum, and I double Q1. Everything doubled, okay? So that's if you multiply by a constant. It affects all the data value, or all the summary statistics. So now, let's see if I can find a purple. So now I decide to count the quiz as 100 points. The way I'm going to do that is I'm going to double all the scores, and then I'm going to add 20. So your score is now 90. Whoops, wrong way. So I'm doubling, so you now have a 90. That really is purple, it's just kind of dark. So I double this, I get 70, and then I add 20. So we got to think about what happens. So my mean, I'm going to double that, which I get 60 over here, and then add 20. So I'm going to get 80. My median, I double it, which gives me 64, and then I add 20, so it's 84. My IQR. Now, you got to be careful, because I'm doing two things. I'm doubling, and then I'm adding. Well, IQR and standard deviations are measures of spread. So the doubling will affect them, multiplying by 2, but the adding 20 does not. So the IQR is going to be 16, because it's going to double but not add 20. The standard deviation, also a measure of spread, is going to double, so it's going to be the 12, but not add 20. Okay, so you got to watch out for that. The minimum is going to double to 24 and then add 20. It's a position, and it's affected by both. Q1, again, is a position, so we're going to double it and then add 20. And those would be my values. So it's important to know it's important to know that adding or multiplying, all the different things we do mathematically to the measures of center are going to change those values. But for spread, only if you are multiplying or dividing will that change that. Okay, so now I have a made-up problem. This is a decathlon, and it's kind of a silly example, but we're going to suppose two competitors tie in each of the first 8 events. In the 9th event, the high jump, one clears the bar 1 inch higher. Then in the 1,500-meter run, the other one runs 5 seconds faster. So who wins? It boils down to knowing whether it is harder to jump 1 inch higher or run 5 seconds faster. So we have to be able to compare two fundamentally different activities involving different units. That's where we're going to use our standard deviations, and we're going to use z-scores. So we can, just like we compared the ACT to the SAT, now we can compare a high jump, and we're going to compare that to running. So if we knew the mean performance by world-class athletes in each event and the standard deviation, we could compute how far each performance was from the mean in standard deviation units called z-scores. So consider the 3 athletes' performances shown below in a 3-event competition. Note that each placed first, second, and third in an event. Who gets the gold medal? Who turned in the most remarkable performance of the competition? So let me get rid of this. So here is our data. So we've got competitor A, who you can see they won shot put. Competitor B had the fastest score on the 100-meter dash. And competitor C looks like they won the long jump. So then how do we know? Well, one of the things we're going to need to do is I want to convert these, since I have feet here, this is pretty easy because notice this is 3 inches out of 12, so this is a quarter. So let's change this to 27.25 feet, and let's change this to 0.5 feet. So now we have our units all in feet for those. Okay. So we're going to calculate z-scores. Remember, to find the z-score, you're going to take the data value, I'm going to call that x. We're going to subtract the mean, and we're going to divide by the standard deviation. So I'm going to be using these values from this chart for my because I have my my means and my standard deviations. So for competitor A, when we are calculating their z-score, we take 10.1 and subtract the mean, which you can look back and see that was 10, and divide by the standard deviation, which was 0.2. And if you calculate this, you will get 0.5. Okay? Let's go ahead and do competitor B, because I want to talk about this, because this one's a little different than the shot put and long jump. But if we look at the z-score for competitor B, we're going to take 9.9 minus 10 divided by 0.2, and I get negative 0.5. And for the last one, I'm going to take, for competitor C, I'm going to take 10.3 minus 10 divided by 0.2, and I get 1.5. Now, remember what a z-score is. A z-score tells us how many standard deviations they are above or below the mean. But we're running a race, and the low score is better. So we kind of have to reverse this. So what I'm going to think about this as, I'm going to actually take this to be the opposite and call this negative 0.5, because we know that this person is the best. So for this one, my z-score I'm going to use is a positive 0.5. So I'm making this the opposite. And this one, I'm making this the opposite. So I'm going to use a z-score of negative 1.5. Because this person B, they ran faster. So they should have the highest z-score because they ran faster than the mean. So that one was a little tricky on that one. So my z-score up here, I'm going to use as negative 0.5. And that was just reversed because it's better to run lower than the mean. So we want to reflect that as a positive z-score. For the shot put, we're going to take competitor A had a 66. If you look back at the average, it was 60. And then we divide by our standard deviation for shot put. So we get a z-score of 2. So why don't you pause this and go through and fill out the rest, and then come back and I'll have the other scores in there. So here are all my z-scores. If you didn't pause it earlier, you can pause it now so you have all those. So then we have to talk about, well, how do we decide who the winner is? So for competitor A, they ran worse than average. They were about half a standard deviation below the mean, or worse than the mean, I should say. But for shot put, they were the best because look, they're the highest above the mean. So they were 2 standard deviations above the mean. Competitor B was right at the mean, and competitor C was only 1 standard deviation above the mean. So all of them were above the mean, but competitor A would win. For the long jump, you can see that competitor C would be the highest because they were 2.5 standard deviations above the mean. But look at how they were over here. They were 1.5 standard deviations slower than the mean for running. So how do you compare those? Well, one thing that we can do that would be pretty easy when we're doing that is we can either average the z-scores or we could just add them up. So if you add up the z-scores, negative 0.5 plus 2 plus 0, I get 1.5. And if I take 0.5 plus 0 plus 2 and get 2.5, and if I take negative 1.5 plus 1 plus 2.5, I get 2. So then we have player B gets the gold, competitor C gets the silver, and competitor A gets the bronze, if those were the top 3 people. Okay, so that kind of gives you a little idea about z-scores, how you can use z-scores to compare. Remember what a z-score is. It measures how many standard deviations your data value is above or below the mean. We saw ways that you can, that adding or multiplying a constant to a data set, ways that it can affect all your summary statistics. So those are all things you need to be familiar with.